Welcome to this course on high speed aerodynamics and also often called as compressible aerodynamics or gas dynamics. We already had a number of courses on aerodynamics in which we have discussed mostly low speed or incompressible flows. And the first question that comes to our mind, that what is special or what is the difference in high speed aerodynamics, that we need to consider high speed aerodynamics separately from low speed aerodynamics. The first and foremost point that is related with high speed aerodynamics, that here the speed of the fluid or say the gas or air is considerably large. How large it is, that quantification we will be doing later on, but we can say in briefly that the speed is comparable to the local speed of sound. And then if we want to maintain a flow at very high speed, obviously the pressure difference or the pressure changes that will be associated are quite large. Now, once the pressure changes are large, the gases is likely to change its density. Rather, we cannot assume that the pressure changes are not capable of making any changes in density, which was the basic assumptions used in low speed aerodynamics or incompressible aerodynamics, where we consider that the pressure changes are so small that there is no change in density as a consequence. However, when the speed is much higher, then the pressure changes are large, and as a consequence there will be changes in density in the pressure, density of the gas due to the change in pressure. And hence the definition of incompressible flow, that is density changes are negligible due to change in pressure, is violated, and the flow cannot be considered as incompressible, rather they have to be considered as compressible flow, where density causes a change in pressure causes a change in density. Also we know that all substance, and that includes gas also, have certain amount of energy due to its existence. Even a gas at rest has certain amount of energy, which we call the internal energy, which is associated with the random motion of the molecules, translation, rotation and vibration of the molecules, which is manifested in the form of internal energy and temperature. Now, a flowing gas, in addition to these random molecular kinetic energy or internal energy, has also a kinetic energy, and when the speed is large, the kinetic energy of the gas is also of the order of internal energy. Even if the speed is very high, it can be an order higher than the internal energy, and as a result, if there is a change in energy, that is from kinetic energy to internal energy, in this case the change can be considerable. In low speed flow, the internal energy, kinetic energy is so small that even if the entire kinetic energy converts to internal energy, there will be hardly any change in the internal energy or temperature. However, in high speed flow, since the kinetic energy is quite large, can even be an order of magnitude larger than the internal energy. So, a fraction of this kinetic energy, if it changes to the internal energy, the change in internal energy will be considerable, and as a result the temperature change will also be quite large. So, this provides a coupling between internal energy and kinetic energy, or the temperature and the flow field, and the two cannot be separated or solved separately, which we saw in low speed case that they can be solved separately. That is, the temperature equation or the energy equation as we found there is decoupled from the other flow equations. But here we see that they are completely coupled. That large change in temperature causes a change in pressure density, and not only pressure and density, but also some other fluid properties that includes coefficient of viscosity or coefficient of thermal conductivity. So, there is a complete coupling between the energy and flow motion. Some additional features may also come in when the temperature is very large, that is when the speed is very large and change in temperature is very large. Due to this large change in temperature, chemical and thermal reaction may occur in the gas, which includes excitation of the vibrational mode, dissociation of the gas molecules, ionization, and if it is a mixture of gases, then some chemical recombination reaction and many such reactions. In such a situation, some additional features also come into the picture. Of course, we will not discuss any of these phenomena in this course, and hence we will not discuss about them further. Also, we will be seeing that in high speed flow, the information, that is the disturbances, propagates in certain directions only, which of course depends on the local Mach number. Unlike the low speed flow, where disturbance propagates in all directions at the same rate, but in compressible or high speed flow, these disturbances will propagate in certain directions only, and the directions depends on the speed, or rather to the ratio of the speed and speed of sound. Since change in temperature, internal energy, and simultaneously also pressure and density are coupled, in addition to the conservation laws that are always used to analyze the flow or discuss the flow, we will be needing some thermodynamical concepts also. This is also a specific difference between low speed flow and high speed flows, that in low speed flows the thermodynamics do not come into the picture explicitly, but in high speed flows the thermodynamics is an integral part of this. That is because the change in internal energy or temperature is considerable. We know that in low speed aerodynamics, we can describe the flow by the basic conservation laws, which are say the continuity or the mass conservation law and the momentum conservation law, and the energy conservation is usually decoupled from these two. That is, the mass conservation and momentum conservation can be solved together, and the result can be used to solve the energy equation for temperature or internal energy. We have already mentioned that in high speed flow, that energy equation is also coupled with this set, and they cannot be solved separately, they need to be solved together. That is, all three conservation laws are linked together. Now, in addition, we also have seen that the pressure, density and temperature are linked together, and some thermodynamical relationship for them is also to be specified. So, what we need, what we saw here or what we discussed here, that to solve high speed flow we need to consider the energy equation in a coupled manner, and also we need some relationship between the properties of pressure, density and temperature. And to do this we need to bring in the subject of thermodynamics explicitly in the discussion of high speed aerodynamics. So, essentially we will start these courses with just a very brief review of the thermodynamical concepts that are useful for discussion in high speed flow. However, as you have mentioned that we will not consider the very high temperature or very high speed flows, where we need to consider the gas as mixture or chemical reactions and other thermal reactions. So, our thermodynamics will not include those phenomena. Now, when we go for a brief review of thermodynamics, the the law of conservation of energy is one of the principal law of thermodynamics, and it brings in the concept of internal energy of a system. Now, what is a system thermodynamically? A thermodynamical system so, let us point out first what we have discussed, that in high speed flow we have discussed that changes in pressure are large that may cause change in density. So, high speed flows are compressible. We also discussed that flow kinetic energy is comparable to internal energy So, kinetic energy may cause considerable change in internal energy or temperature. And of course, and vice versa. This implies a strong coupling between temperature and flow velocity, or of course we can say internal energy and kinetic energy. When speed is very high, the temperature rise may be also very high, and thermal and chemical reaction reactions may occur. But will not be discussed in this course. These are of course very easy to comprehend from our basic discussion that we had. However, we have one more very important phenomena, that disturbance or information propagates in certain direction only. Of course, this is not straightforward from this discussion as we had now. However, this will be seen later. So, based on these basic differences, what we see that thermodynamics is an integral part of high speed aerodynamics or gas dynamics. Now, as we mentioned that the physical basis of thermodynamics are formalized in certain conservation laws, and the law of conservation of energy is one of these principal law. And this law of conservation of energy introduces the concept of internal energy. So, concept of internal energy brought in by physical law of conservation of energy. Now, thermodynamics deals with what are called as system and surrounding. So, what is a system or what is a thermodynamic system? We may recall that the thermodynamic system is basically a certain quantity of matter separated from the surrounding or the environment. So, a certain quantity of matter separated from the surroundings or environment by an enclosure. Of course, this enclosure is just a closed surface whose property is known everywhere. It is not necessarily to be a physical rigid enclosure. So, enclosure is just a surface or rather a surface, closed surface whose properties are defined everywhere. That is, this enclosure, it may transmit heat, work, mass or any momentum or any such thing. So, enclosure may or may not transmit heat, work, mass, momentum and similarly other such properties. Now, thermodynamics starts with defining the system, its surrounding or environment and its enclosure, and the changes in any thermodynamical properties are considered in the within the system. Now, classical thermodynamics is basically concerned with equilibrium state of uniform matter. So, classical thermodynamics is so let us say classical thermodynamics concerned with only equilibrium state of matters. Thermodynamics concerned with equilibrium states of the system. That is the state in which all local, mechanical, physical and thermal quantities are virtually independent of position and time. Equilibrium states, that is the states in which mechanical, physical and thermal quantities are practically independent of position and time. So, obviously, that thermodynamical results or the results from classical thermodynamics can directly be applied to fluid at rest. Now, question comes that if the fluid is flowing, how can the classical thermodynamics be applied? Because now it is not in equilibrium. So, however, it is observation that departure from equilibrium in a moving flow, in a moving fluid are practical or small as regard to their effect on the thermodynamical relationship. So, for a flow, so the departure from equilibrium in a flow even at high speed as regard to their effects on thermodynamic relations. That is, even though it appears that the departure from equilibrium is quite large, but as far as thermodynamic relationships are concerned, the effect of these departures are quite small. That is, the relations that we derived for equilibrium states can be used for flow also. So, results from equilibrium states can be applied moving fluid. So, what happens that fluid mechanics of perfect fluids are basically an extension of equilibrium thermodynamics to moving fluids. Now, so what we say that fluid mechanics is an extension of equilibrium thermodynamics to moving fluids. Now, if we want to consider the conservation of energy, as we have already mentioned that we have to consider the kinetic energy also, and if we try to find a ratio of this kinetic energy say per unit mass to the internal energy per unit mass, is basically a dimensionless quantity, and as we will be seeing later that it is directly proportional to the square root of Mach number. Where Mach number is the ratio of the flow speed by speed of local speed of sound. So, this can be very easily shown that the ratio between kinetic energy and internal energy is proportional to square of Mach number. That is, so the internal energy is of course proportional to the square of the speed. So, kinetic energy is proportional to v square, where v is the speed and internal energy, which we will be denoting by E, so the ratio is proportional to A is speed of sound, E is internal energy, so this ratio is V square by A square. Anyway, let us come back to our discussion on thermodynamics. Now, thermodynamics says that for a pure substance, the state of a system can be specified by any two thermodynamical properties. So, for a pure substance, a thermodynamic state of a system can be expressed by two state variables. Now, what are state variables? Now, state variables in the thermodynamical context is defined as those variables which comes back to its original value or original magnitude if a cyclic change is allowed to happen in the system. That is, starting from one particular state and then we change the state, of course, in such a manner that equilibrium is always preserved, and then come back to the same state at the end, then there are certain variables whose magnitude will again come back to that original value. So, these are called state variables. Now, for convenience, these are usually take pressure P and specific volume, that is volume per unit mass, which of course is reciprocal of the density, are the two variables. Then any other state variables are can be just a function of these two state variables. All other state variables are function of these two. That is, let us say T as an example, T temperature, which is also a state variable, is a function of pressure and volume, or we can of course write we should also define in this context the intensive and extensive variables. Extensive variables are those which depends on the mass of the system, and intensive variables are those which are independent of the mass of the system. Say as an example, pressure is independent of the mass of the system, the temperature is also mass of the system. However, the volume is of course depends on the mass of the system. But again, if we consider the specific volume, then we have volume per unit mass, which is of course independent of the mass of the system. So, we see that for every extensive property which are independent of mass, there is a corresponding specific quantity which is per unit mass, is of course and is independent on mass, and hence intensive quantity. Now, let us try to bring in the concept of temperature from thermodynamical sense. So, this is the concept of thermodynamics, or sorry, concept of temperature comes in this way, that which can be called the Zeroth law of thermodynamics, or the concept of temperature. What it says that a mass of fluid in equilibrium has the same temperature as a test mass of fluid also in equilibrium, and if the two masses remain in equilibrium when placed in thermal contact. That is, if we write, let us say a mass of fluid, of course, it need not be fluid, it applies to any other substance. A mass of fluid in equilibrium has the same temperature as that of a test mass, of fluid which is also in equilibrium. And if the two masses remain in equilibrium, when placed in thermal contact. That is, let us say that we have two masses of fluid, both are in equilibrium, and we placed them in contact such that heat can flow from one to other, and if the equilibrium is not disturbed, that is, if no heat flows from one to the other, then we can say that both the system has the same temperature, or the property which remains which is same for both of these systems is called temperature. Now, we have already expressed that if we have defined two state properties. So, for a pure substance all other state properties are function of these two state properties, which we have formally written as f as function of p v t 0, and this equation is usually called the equation of state. This also exhibits the arbitrariness of the choice of two parameters. That is, instead of taking pressure and volume as the two independent variables, we can take some other state variables, many other states variable will be defined subsequently, and we can take any two of them to express the third one. This relation generally written as P equal to function of V and T and called thermal equation of state. Now, another important quantity that describes the state of the fluid is the internal energy per unit mass. Internal energy per unit mass. And already you have seen that discussed that this internal energy is basically the manifestation of the random molecular motions, and essentially this is the kinetic energy of the molecules moving at random, moving in translational, rotational and vibrational motion, and that total kinetic energy associated with all the molecules in a system which are moving at random is manifested as the internal energy of the system. Now, now the first law or the conservation of law, first law of thermodynamics gives change in internal energy of the system at rest change in internal energy of the system at rest due to change of state. Now, the change is such that the conservation of energy is satisfied when we consider both heat given to the fluid and work done on the fluid. Change satisfies conservation of energy if both heat given to the system and work done on it are accounted. Let us say that heat gained per unit mass is Q and the work done on the fluid is W per unit mass. Heat gained per unit mass equal to Q, work done on system per unit mass equal to W. Then the first law simply says that first law of thermodynamics. So, in our earlier equation of state where we considered pressure, volume and temperature, if we consider internal energy, that is if we write the equation of state as called caloric equation of state. Now, we see here that we have defined internal energy is E is a state variable, that is change in E depends on the initial and the final state. However, Q and W, that is the heat added and work added, are external effects and they depend on the particular way in which the transition as between the two states is made. So, E is state variable depends on initial and final state only.
and depend on the path that the transition has taken. That is, the amount of heat and work that are required, of course, depends on how the change has been brought in, from starting from one initial state to a second final state. The energy, internal energy depends only on these two states, irrespective of how this transition has taken place, while this heat added and work done on it depends on how these changes have been brought in, what are the intermediate states through which the process has gone. And however, this change in or the Q and W would be such that the sum total will be independent of the path. We will continue this discussion in our next class of review of the basic thermodynamics and some very basic relationships coming out from thermodynamics, which will be useful for our future discussion in high speed aerodynamics.